Kia ora team, welcome to this Level 2 Chemistry 2023 Chemical Reactivity exam. Let's go through this exam, see how we go, and prep for your end of year examinations. So question 1, the acid found in human stomachs is primarily hydrochloric acid and has a pH value of approximately 1.5. Calculate the concentration of hydronium ions present in a hydrochloric acid solution of pH 1.5. When you look at your resource sheets, we see this equation over here, which allows us to calculate the hydronium ion concentration. That's what the square bracket means. So we've been given the pH, we can simply plug that into this pH over here in the equation, plug this into our calculators, and then we should get 0.316 moles per litre as the hydronium ion concentration. Please remember your units and always remember that it's usually 2-3 significant figures. Okay, that was worth and achieved. Next question. Fast-acting paracetamol tablets contain sodium hydrogen carbonate, which reacts with stomach acid. The equation is shown below over here. Some students wanted to investigate how long it takes for all the sodium hydrogen carbonate in paracetamol tablet to react in a human stomach. They conducted an experiment where 0.25 gram tablet of sodium hydrogen carbonate was reacted with an excess of hydrochloric acid at room temperature, approximately at 20 degrees Celsius. The volume of CO2 produced during the reaction was recorded and graphed below. With reference to collision theory, I might just highlight that. With reference to collision theory, explain why the steepness of the line changes as the reaction proceeds. Refer to section A and B in your answer. Okay, so let me just go through this question and explain what's going on here. So what do we notice? At the start of the reaction, over here in section A, we can see that the steepness of the curve is quite steep in relation to section B. So why is that the case? Well, in section A, you should understand that there are going to be a higher concentration of reactant particles at the start of the reaction. As the reaction goes on, that concentration decreases because these reactants have collided to form products. So there are less available reactants to collide with to form the products, which means the rate of reaction actually slows down. Okay, in comparison to the start of the reaction. And then right at the end, it levels out because all of those reactants have collided to form products, and that's the end of the reaction. So to put this in words, let's talk about section A first. Section A shows a steep curve, which indicates a fast rate of reaction. So we're always linking back to the rate of reaction. This is because during the start of the reaction, the concentration of HCl and NaHCO3 are high. So I'm very specific to the actual equation. It's important for you to be specific to the actual context. A high concentration of these reactants result in more frequent collisions per unit of time. It's important to state per unit of time so that we can have a definitive time bound. And therefore, a faster rate of reaction as indicated in the steepness of section A. So remember, the key thing here is to refer to the context, refer to the actual chemicals in the reaction and the section of the graph, linking steepness of the section to rate of reaction. Okay, now to look at section B. Now feel free to pause and see what you would write and then compare it to what I have written, but let's have a look. During section B, the curve is less steep, which indicates that the rate of reaction is slowing down. This is because the concentration of HCl and sodium hydrogen carbonate decreases over time as they react to turn into products. As the concentration of these reactants decreases, there are less frequent collisions. So we're linking back to what the question has asked us over here in terms of collision theory per unit of time. This is reflected in section B. Okay, that would have earned you a merit. So we've talked about everything that has been highlighted and referred to the graph and the actual chemicals in the equation, and that should get you a lovely merit. Okay. The internal temperature of a human stomach is approximately 37 degrees Celsius. Explain why the student's experiment would not give a good indication of how long sodium hydrogen carbonate in the tablet takes to react in the human stomach. Refer to collision theory in your answer. So basically, these students are conducting an experiment outside of the human stomach, and they want to know if this will be a good indication for how long this tablet takes to react in this human stomach. Why isn't this a good idea? Well, let's state the obvious. So the experiment is carried out in room temperature, which is 20 degrees, as stated in the question. Okay? So this does not reflect the true rate of reaction taking place in the stomach, which is 37 degrees. The temperatures in both environments are different, so how can the experiment carried out in room temperature be a good reflection of the reaction that's actually happening in the stomach, right? So let's delve into this a little further by talking about collision theory in the stomach, okay, and then this can basically show why it's not going to be reflective for this experiment to be carried out in room temperature. Okay, so the stomach has a higher temperature of 37 degrees, which results in a faster rate of reaction. Why? Because higher temperature results in HCl and sodium hydrogen carbonate gaining more kinetic energy. As these reactants move around more, there are two things which happen to the rate of reaction because of this increase of kinetic energy due to heat. 1, this increases the frequency of likely collisions. If there's an increase in kinetic energy due to a higher temperature, the particles are going to be buzzing around a lot faster and increasing the likely collisions with surrounding particles, which increases the rate of reaction. Okay. Secondly, another way increase in temperature allows for a faster rate of reaction is by accounting for a greater proportion of collisions having enough energy to overcome the activation energy. Okay. So there'll be more collisions between the particles, okay, between these specific particles, okay, HCl and sodium hydrogen carbonate, and more of those collisions will have enough energy to overcome the activation energy. Remember, the activation energy is the minimum amount of energy needed to kickstart a reaction, okay? So these are the two reasons you have to know in relation to temperature and how this impacts the rate of reaction, and you have to discuss them, okay? Don't say that a greater proportion of particles have enough energy. It's the collisions, key point. This means a greater rate of successful collisions and an increased rate of reactions per unit of time, important to have that in the stomach, than the experiment. So we have linked back to the context, okay, on why it wouldn't be a good idea or it wouldn't be a good indication to carry out this experiment in the room temperature environment. So that's how we answer this question, and that is worth an excellence. Okay, part C. While the acid found in human stomachs, hydrochloric acid, is considered a strong acid, propanoic acid is considered weak. With reference to these two acids, explain the difference between strong acid and a weak acid, okay? And these are what we're dealing with. Okay, so this question shows that HCl is a strong acid, and then propanoic acid is weak, okay? So we have to discuss the difference between these two things. So let's have a look at the clues that I have, which will come in handy very soon. So for a strong acid, okay, we have to show the reaction with a single arrow, okay. For a weak acid, we have to use this equilibrium arrow to show that the reaction can go in both ways. Okay, before we get to that part on writing reactions, let's have a look at what you should write. So you should start off by saying, a strong acid, what is it going to do in solution? It fully dissociates in water. So when writing up the reaction, we want to show HCl, which is the strong acid we're dealing with, reacting with water to dissociate. Okay, so we've got the HCl over here in water, okay, and we use a single arrow because it's a strong acid. What it's done is it's donated its hydrogen to the water, because acids are hydrogen donators. While donating a hydrogen to the water, it has formed H3O+, because this is an extra hydrogen from the HCl. So that hydrogen that's been donated leaves behind a Cl-. The reason why it's minus is because it's lost a hydrogen which is positively charged. It's important to include these little symbols over here, aqueous, sorry, and the charges, okay? So this is how you write the reaction of full dissociation of a strong acid. Okay. Next thing. A weak acid, like propanoic acid, what is it going to do in water? It's going to partially dissociate in water, okay? Which is why we have to use an equilibrium arrow in the reaction, because it's only partially dissociating. Some of this acid is still intact, okay? So here we have propanoic acid in water, and then because it's still an acid, it's still going to donate a hydrogen, okay? But not as much or not to the same extent as the HCl. So this hydrogen gets donated to H2O to form H3O+ ions, okay? And then because we've lost this H to the H2O, it becomes this COO- on the end, okay? It's important to include that minus because it shows that we've lost the positive hydrogen. And that's our reaction for the dissociation of a weak acid. Compare and contrast the pH and electrical conductivity of hydrochloric acid and propanoic acid solutions which are of equal concentration. Okay, so I have some points down the side just to structure our answer well. So what we want to do is let's highlight the key points. We want to talk about pH, electrical conductivity of hydrochloric acid and propanoic acid. So these are the 4 things we need to talk about. All right, so let's have a look. First, let's talk about electrical conductivity and what that depends on. Electrical conductivity depends on the concentration of free-flowing ions or charges in a solution. Whoops. That's the end of school, team. Anyways, electrical conductivity depends on the concentration of free-flowing ions or charges in a solution, okay? pH, okay, in general, depends or is a measure of the concentration of hydronium ions, which is H3O+, okay? So the more H3O+ ions there are, the more acidic something is. The less hydronium ions there are, the weaker the acid is, okay? So let's look at HCl, and then we also have to link HCl to conductivity and pH, as I've indicated over here. So, since HCl is a strong acid, it fully dissociates in solution which results in a high concentration of free-flowing ions. So dissociation means to break apart, and so because HCl is a strong acid, it fully breaks apart, which means that there are more free-flowing ions. There's a higher concentration of them. This means that HCl in solution has good electrical conductivity. Okay. So we've done conductivity. Let's talk about HCl and pH as the question states. In terms of pH, HCl dissociation results in a higher concentration of H3O+, which means a lower pH. Remember, a low pH is associated with higher acidity. Okay, so the more H3O+ ions there are, means a lower pH, more acidic. Okay. Now, this is a compare and contrast question, so it's important to include this sort of terminology. In contrast, let's look at propanoic acid. Let's look at the conductivity. Propanoic acid is a weak acid and only partially dissociates in solution. So this results in a lower concentration of free-flowing ions because it's not as broken apart as HCl. This means poor electrical conductivity in comparison to HCl. Cool, we've done conductivity, let's look at pH. So additionally, propanoic acid accounts for less production of H3O+ ions because it only partially dissociates, remember? So because of that lower concentration of H3O+ in solution, this means a higher pH, okay? So a higher pH means that it's less acidic than HCl. So it's important to wrap your head around the fact that with more H3O+ ions in solution, you're going to get a higher pH value, okay, which is less acidic than basic, okay? All right, and that concludes question 1. All right, moving into question 2. The molecule lactose, which is found in milk, is slowly broken down in the stomach by water into sugars, galactose and glucose. The rate of this reaction is significantly increased by the presence of an enzyme called lactase. The lactase is not used up in the reaction. So whenever something is not used up in the reaction, you can be very sure that it's going to be a catalyst, okay? So lactase is a catalyst. Okay. Complete the energy diagram below by drawing 2 lines to show the reaction with and without the addition of lactase. So here I've gone ahead and drawn 2 different lines. So this red line over here, okay, is showing how much energy is needed to form the products from reactants. Okay, and so these 2 lines, take a minute to test yourselves and see which one is the line that represents the involvement of lactase and without lactase. Okay, so here we have it. This red line indicates the lack of lactase, okay? Whereas this dotted blue line indicates the presence of the lactase enzyme, which acts as the catalyst. All right, the reason why this diagram is drawn the way it is because lactase, all right, which is a catalyst, provides an alternative pathway with a lower activation energy. Okay, so less energy is required following this pathway for this reaction to actually occur. Okay, so now that we have labelled our diagram as the question has asked us to, we can move on to the next question. Explain how the rate of reaction is altered by the presence of lactase enzyme. Refer to collision theory and activation energy in your answer. Okay, so these are the things that we need to talk about in our answer. Let's try tick these off. Okay, so let's first of all talk about the lactase enzyme as a catalyst. The catalyst lactase provides an alternative pathway which requires a lower amount of activation energy. The activation energy is the minimum amount of energy needed for the reaction to happen. Okay, so I've talked about the lactase enzyme in context of it acting as a catalyst. Next thing that we need to talk about. Okay, the addition of lactase causes the rate of reaction to speed up because more particles have energy to overcome the new activation energy threshold. So there we go, we've talked about the rate of reaction and how it speeds up when lactase is introduced. And we've also mentioned how that happens. Let me go into more depth as to how this happens, okay? So the rate of reaction speeds up because more particles have enough energy to overcome the new activation energy threshold. What do I mean by this? Well, as we can see with the blue dotted line, there is a new threshold for the amount of energy the particles need for the reaction to happen, and it seems to be a lot lower, okay? So, with a lower activation energy threshold, more particles can actually react and overcome this energy, which speeds up the rate of reaction basically. An analogy I like to think about is NCA. If we made NCA easier, aka lower the threshold for passing or getting excellence, more students will be able to pass the exams or gain endorsement, okay? So that's what I see catalysts as. They lower or they provide a lower activation energy threshold, the alternative pathway. So more particles can overcome that threshold with minimum activation energy. Okay, so let me reinstate. With the addition of lactase, the rate of reaction speeds up because more particles have energy to overcome the new activation energy threshold, okay, which is a lot lower than the previous activation energy threshold. Okay, so we've talked about the activation energy over here, cool. We've talked about lactase enzyme, rate of reaction. Last thing we need to talk about and refer to is collision theory. This means that there are more collisions per second, which results in a higher rate of reaction per unit of time. Okay, it's important to include things like per second or per unit of time to give a nice set of bounds for the reaction. Okay, otherwise it could happen forever and ever. All right, so I've ticked off all the key points of the question. Okay, part B. The steam methane reforming process, which is one of the primary means of producing hydrogen gas, is shown below. Write the Kc expression for the reaction. Okay, just a reminder, Kc is an equilibrium constant, which shows the proportion of products to reactants during equilibrium. And equilibrium is when the forwards rate of reaction is the same as the backwards rate of reaction, okay? So once that equilibrium spot is hit, Kc shows us the proportion of products to reactants. And so the expression goes something like this. So we've got the products at the top of the fraction, and then we've got the reactants at the bottom of the fraction. Okay, so it's products over reactants. So for the products, we've got CO over here, and because it's a gas, we can always include gases in the equation, but we cannot include pure solids, okay? So we've got CO, and then we've got 3H2. Here's something that you should be mindful of. When writing the expression, these big numbers always turn into subscripts, okay? So we've got H2 to the power of 3, okay? Always include square brackets, not round brackets, because square brackets mean concentration. Down below, I've popped in the reactants in their square brackets. And that's just the Kc expression. That's all we need to do for the expression. No maths involved for this because they haven't given us any values. Okay, explain using equilibrium principles why removing hydrogen gas as it forms is advantageous in the production of hydrogen gas. So the first thing that we need to do is state Le Chatelier's principle. What is Le Chatelier's principle? Who can remember? Le Chatelier's principle states that when a system is disturbed, the position of equilibrium will shift to counteract that change or disturbance to restore equilibrium, okay? So equilibrium is kind of looking at counteracting or doing the opposite to the disturbance, okay? It's trying to counteract the disturbance or change, bring it back to the regular equilibrium. So in context to H2 being removed, okay, this guy, if this is removed, that's a disturbance to the system, isn't it? So equilibrium actually wants to increase its production in compensation for it being removed out of the system. So what is it going to do? Well, it's going to have to drive the forward reaction. It's going to have to drive the forward reaction so more products can be formed to restore equilibrium or restore the lost or removed hydrogen gas. Okay, so let's see what I've written. When H2 is removed from the product side, the equilibrium will favour the forwards or the right-hand side reaction to produce more H2 in compensation for its removal. Therefore, the removal of H2 as it's produced is advantageous because it prompts the forward reaction to produce more H2. So I've linked it back to the context, the initial question. Cool. All right, this one's going to be a little bit more high-end in terms of thinking, but we got this. All right, at high temperatures, the value of Kc increases. Explain using equilibrium principles whether the forwards reaction is endothermic or exothermic. Okay, so we've got a few clues that the question has given us. We just need to unpack it a little bit before we delve in. So at higher temperatures, the value of Kc increases, okay? So let's have a look at this diagram over here, okay? Kc, an increase in Kc indicates that there's going to be more products than reactants, okay? This is because Kc is a fraction, so any fractions which are top heavy means that it results in a big number, greater than 1, okay? So, as we can see here, because Kc increases, we have to understand that the forward reaction must be favoured because that's what accounts for the increase in products and hence the increase in Kc. Okay, it's not going to be the backwards reaction because that would increase the reactants, which would result in a small Kc. So, increased products due to the forward reaction being favoured results in an increased Kc. So we know that the forward reaction is being favoured. Okay, so the next part we have to unpack is high temperature, which is being induced. Okay, so this is the change or the disturbance. So because the temperature is increasing, of the surrounding temperature of the reaction is increasing, equilibrium wants to counteract this by decreasing the temperature back down to restore the equilibrium. So what is it going to favour? Is it going to favour the exothermic reaction or the endothermic reaction? How is it going to decrease this increase in temperature? Well, it is going to favour the endothermic reaction because the endothermic reaction is going to absorb this added heat and cool down the surroundings. If the exothermic reaction was favoured, exothermic involves releasing heat to the surroundings, which will only heat things up even more, okay? And in temperature type situations, we're always concerned with the surrounding temperature, not the temperature of the actual reactants or particles, okay? We're always looking at the surrounding. Okay, so increase in temperature, equilibrium wants to counteract that, so it's going to have to decrease the temperature by favouring the endothermic reaction to absorb that added heat. Endothermic means absorption of heat. Okay, so how do we put that into words? Well, let's start off with explaining what Kc actually is. So Kc is the equilibrium constant, and it measures the proportion of products to reactants. Okay, Square brackets means concentration. The increase in Kc indicates that there is a greater proportion of products to reactants, which means the forward reaction must be favoured. Okay. As the temperature of the system increases, the system will respond to decrease the added heat. Okay. This is possible by favouring the endothermic reaction, which absorbs heat to cool or decrease the surrounding temperature back down, and that's what will restore equilibrium. Therefore, bearing in mind that the forward reaction is favoured as indicated by the increase in Kc, this forward reaction has to be endothermic, okay, to absorb that added heat. So we've put all of our clues together with our increase in Kc and high temperatures to come to this conclusion over here, okay, that the forward reaction is being favoured and it has to be endothermic. Okay. Question 3. Alright, we're up to part 3 of the exam. Well done if you made it this far. Okay, both water and hydrogen carbonate are amphiprotic, meaning they can act as either an acid or a base. The reaction of hydrogen carbonate with water is shown below. So, it's asking us identify the two acid-base conjugate pairs in the reaction of hydrogen carbonate with water. Okay, let's do it in this order: acid to base conjugate pairs. Okay, something that you should know is that acid-base conjugate pairs have a difference of 1 hydrogen. Okay. So if we're looking at the first pair, let's look at hydrogen carbonate. As you can see here, hydrogen carbonate in its acid form is over here. Acids are hydrogen or proton donators. So the reason why this is an acid, because it has a hydrogen that it's able to donate. Okay. This over here, however, carbonate, is going to be the base because it has the tendency to accept a hydrogen. Bases are hydrogen acceptors, okay? So this makes an acid-base pair. If we look at the next pair, it's going to be between hydronium and H2O. Hydronium is the acid because it has a hydrogen which it can donate. H2O is the base in this instance because it has the ability to accept an extra hydrogen. Okay, so just remember, difference of 1 hydrogen. Acids are proton or hydrogen donators. Bases are hydrogen acceptors. B. A 0.1 mole per litre solution of the weakly basic salt, sodium ethanoate, has a pH of 8.88. We know that this is going to be a basic salt because it's got a metal component and a non-metal component, okay? And it's a weak basic salt, sodium ethanoate. Write the equations below to show the dissolving of sodium ethanoate in water, okay? So dissolving, whenever you come across the keyword dissolving, this essentially means how it's going to break up into its ions, okay? So in water, we've got sodium ethanoate. It is going to break up into its ions as shown over here, okay? So the reaction that follows, which results in a basic solution, is the next reaction that we have to write up. So to show that it's resulting in a basic solution, basically, see what I did there? We have to take the base part of the reaction above and plug it into this next equation down here, okay? So what's happening is it's going to accept a hydrogen from H2O, okay? And that's shown over here. It's accepted that hydrogen from the H2O, And because the H2O has lost that hydrogen, it is going to form OH minus ions. And we know that this is a basic solution because of these OH minus ions formed, all right? This wouldn't have worked as well if we took the Na plus. So you got to take the right ion from the equation above, okay? And it's usually going to be the one that's able to accept a hydrogen, okay? So, next question. A solution of potassium hydroxide of equal concentration has a significantly higher pH than sodium ethanoate solution. Calculate the pH of a 0.1 mole solution of potassium hydroxide. Okay, pH calculations. In your resource sheet, you are going to get these two equations. We need to calculate the pH of potassium hydroxide. So to calculate pH, this is the equation over here. However, we don't have the concentration of hydronium ions, we have the concentration of OH minus ions from the KOH. So we cannot use that in the hydronium ion concentration in this part of the equation. So how do we find the hydronium ion concentration when we only have the OH concentration? Well, we have to use this KW equation, okay? The KW equation has the concentration of hydronium ions and OH minus ions, which equals 1 times 10 to the power of negative 14, okay? So the proportion of these ions, okay, equals the KW, which is a constant. It's always going to be 1 times 10 to the power of negative 14. Okay, so what we can do is we can substitute in the OH minus concentration into here. We can substitute 0.1 into here, rearrange to find H3O plus, okay, and then we can plug it in to the H3O plus concentration over here to work out the pH. Okay, so first things first, let's substitute everything that we have. So we know that KW is always going to be 1 times 10 to the power of negative 14. We don't know the hydronium ion concentration yet, but we do know that the OH minus concentration is 0.1 based on what they've given us here. Once we've substituted everything in, we can do a bit of rearranging. So to get rid of the 0.1, what we do is we divide this side by 0.1, and that means we have to do the same to the other side over here. Okay, so it cancels it out on this end, and we are left with H3O plus equals 1 times 10 to the power of negative 14 over 0.1. Plugging that into our calculator, we get 1 times 10 to the power of negative 13 as our hydronium ion concentration. But we're not finished yet. We have to plug this into the pH equation. So by doing so, we get pH equals negative log times 1 times 10 to the power of negative 13. Plugging that into your calculator, you get a pH of 13. Okay. So KOH, just to finalize your answer, you could say that KOH, as shown by the calculations, has a pH of 13. Remember, the higher the pH, the more basic it is. So it shows that KOH is very basic, okay? Very basic, so it's a strong base. Okay, next question. Justify the difference in pH of the two solutions. What are the two solutions again that we're dealing with? Well, we've got KOH and we've got sodium ethanoate. Both of these are basic. KOH is very basic, as we've calculated here. Sodium ethanoate, what does the question tell us? Well, it says that sodium ethanoate is weakly basic, okay, and it has a pH of 8.8. So keeping in mind these two pH values, let me write it down actually. So I don't like that. KOH has a pH of 13, and then sodium ethanoate ooh, I wrote that wrong, my bad. Sodium ethanoate has a pH of 8.8, okay? So we're going to have to compare and contrast these. Both of them are bases. One is stronger than the other. So that's important information for how we're going to write our response. But before we get there, let me just have a moment to just recap, teach you a thing or two, and remind you about acidic, basic, and neutral solutions and the ion concentrations within it. So in a acidic solution, you're going to have a high concentration of H3O plus ions and a low concentration of OH minus ions. So the proportion is going to be like this, okay? The proportion in a basic solution, the proportion of H3O plus ions, H3O plus ions is going to be lower than the hydroxide ions over here. So in a basic solution, you're going to have more OH minus and less H3O plus. In a neutral solution, you're going to get equal concentrations of these two ions, okay? And that's what equals the Kw, all right? So in this instance, both of the molecules that we're dealing with are basic, okay? So how are we going to distinguish between both of them? Well, as I mentioned before, KOH is strongly basic because of the pH 13, okay? Whereas sodium ethanoate is just mildly basic or weakly basic. So how are we going to write about this? Well, let's start off by explaining what pH is all about. pH is a measure of hydronium ion concentration. The higher the concentration of H3O+, the lower the pH, which means it's going to be more acidic if it's a low pH. The lower the concentration of H3O+, this results in a higher pH, which is more basic, okay? So when we're looking first of all at KOH and its pH, you have to understand that KOH is a strong acid and will fully dissociate in water into its ions, okay? And I've written that equation here. As a result, there's a high concentration of OH minus in the solution, as we can see here, because it's a strong base. This means that because there's a high concentration of OH, there's going to be a low concentration of H3O+. This corresponds with a high pH of 13, okay? So that's very well explained. Make sure you wrap this around your head that if you have a high OH minus concentration, you're going to have a low H3O plus concentration, which means a high pH, okay? So, okay, remember we are comparing and contrasting, so the next thing we're talking about is our sodium ethanoate. In comparison, sodium ethanoate is a weak basic salt, okay? So it has two steps. Because it's a salt, remember there's a two-step equation to this. There's two parts. So initially it fully dissolves in water. Remember, dissolving means that it's broken apart. Okay, so in water, as you can see here, it's dissolved into two components. Then it behaves as a weak base in water, okay? So because it's a weak base, it's only going to partially dissociate, as we can see here, okay? So it's given in this equation that the H2O is going to give its hydrogen to this what used to be sodium ethanoate, okay? And because this is basic, it's going to accept that and turn into its conjugate acid. As a result of H2O donating its hydrogen, it's going to turn into OH minus, which shows that this is going to form a basic solution. But because it's weakly basic, it's only going to result in partial dissociation, which means that there's going to be less OH minus ions in comparison to KOH, which fully dissociates. Okay, so only a small amount of OH ions are produced due to partial dissociation. This means that there are more H3O ions by comparison to KOH. Okay, it's still basic, but in comparison to KOH, there's going to be more H3O plus ions. Final part, which is the link. This is why sodium ethanoate has a lower pH, 8.8, than KOH, pH 13. And that is that. All right, next part. The Kc expression for a reaction at equilibrium is shown below. Okay, so remember, Kc is products over reactants. The Kc in this instance, the equilibrium constant in this instance, is 2 at 1,000 degrees. Using the Kc expression above, write the equation for this reaction. You can assume all species in the reaction are present in the Kc expression above and are all gases. Okay, I will highlight that. Are all gases. Okay, so let's write an equation or expression for this, okay, reaction. As I said before, products are on the top. Products are on the top. So whatever's on top is going to be on the right side of the equation, and the reactants are on the bottom. That means they go on the left-hand side, okay? As you can see, based on this expression, that it's got the equilibrium arrow, and that's because Kc is all about equilibrium. Okay, it's an equilibrium constant, so you have to draw the equilibrium arrows, and it said that they're all gases, so I've specified that over here in little brackets. The reason why I have a big 2 in front of COF2 is because of this little subscript, and that shows you that there's actually 2 moles of this, so it's important to include that. But this is basically how you write the reaction. The reaction was carried out at 1,000 degrees Celsius and allowed to reach equilibrium. The concentrations of all the species were then recorded. If the concentration of CF4 and CO2 were found to be equal to one another, and COF2 was 0.105 moles per litre, calculate the concentration of CF4 at equilibrium. Okay, so first things first, we need to write the equation that we're using, the Kc expression. Okay, so this is basically the same as what we have up top. I've just rewritten it down here. The next thing that we have to do is we have to substitute in the values that we do know of. According to the information that's been given, up top it shows that Kc is 2, so substituted that in here. Then the COF2 is shown to be 0.105 moles per litre, so I've substituted that in here. Do not forget the little subscript. Because it tells us that CF4 and CO2 are found to be equal to one another, I have popped them down as X's, okay? The reason why they're X's is because we actually don't know the concentrations of these. We're not given these. We're going to have to find out one of them. But because they're equal, we know that they're both the same, so I've made them X. Next step is to the next step is to simplify the equation. So I know that 0.105 squared is going to be this value over here. Sorry, I don't know that. I put that in my calculator. And then x times x is going to be simplified to x squared. Then what I can do is rearrange to find what x squared is, and the way I do that is by swapping the x squared out with the 2. So in algebra, whenever you have the bottom part of the fraction unknown, you can swap it with the known part on the left hand side of the equal sign. So a little trick for you And then once you rearrange, you can carry out 0.011025 divided by 2. And it shows that x squared is 0.055125. But we don't want x squared. We just want to know what one of the x's is. So the way we get rid of the squared is by square rooting the answer. And then when we pop that in our calculator, it is 0.0742 moles per litre. And I've done that to 3 significant figures. These zeros aren't considered significant, so I have to write these. And I've included units. But that basically, we're not finished yet. I was about to say that basically concludes the exam, but not so fast. We've got one more question left. Explain what effect, if any, increasing the pressure of the system would have on the position of equilibrium. Okay, let me have a bit of a teaching moment here. So if we increase the pressure of the system, okay, equilibrium will want to counteract that increase by bringing the pressure back down. How is the pressure brought back down? Well, the system will favour the side with the least amount of moles, because less moles means less pressure. So in this diagram over here, if we increase the pressure, okay, we're going to have to bring that pressure back down by favouring the side with the least amount of moles, okay, So, in contrast, if we decrease the pressure of the system, equilibrium will want to counteract that by increasing the pressure back up. So, it does this by favouring the side with more moles, because more moles creates more pressure, okay? So, let's have a look at the equation that we're actually dealing with. The equation that we're actually dealing with over here, let's see what happens if we increase the pressure. Which side has more moles or less moles? Well, as we can see here, we've got 2 moles on the reactant side, and we've got 2 moles on the product side. So the moles are actually equal on either side. So even if we increase or decrease the pressure, there's not going to be one side which is favoured more or less, okay? So let's have a look at what to write. First of all, I've gone ahead and said when pressure is increased, usually the system would respond by favouring the side with the least gaseous moles. Gaseous is an important word to use, okay, in this context whenever we're dealing with KC. Okay, where was I? So, when pressure is increased, usually the system would respond by favouring the side with the least gaseous moles to decrease the pressure, hence counteract the disturbance to restore equilibrium. Okay? But, more in context to the question, since both sides of the reaction have 2 gaseous moles, which are equal on either side, the position of equilibrium is unaffected when pressure is applied or added to the system. Okay, and there we have it. That's how we do an exam paper. Hope you learned something new. Please feel free to ask any questions, email me, and we should be good to go.